dynamics of atomic clouds, fractional quantum Hall models on lattices, and anions. So we'll be very curious to hear from you. So let's please welcome Dr. Patra. Thank you.
Thank you very much. Thank you. Thank you very much, Dr. Khan. And so let me first share my screen. Okay, can you see the screen?
Yeah, it's fine.
All right. Okay, so I must start the talk by thanking all the organizers for undertaking such a major endeavor, and quite successfully, I might add. And I should also thank you for giving me this very nice opportunity to present our work on single shot determination of quantum phases via continuous measurements. And also, as Dr. Khan mentioned, I have done my master's at IISER Kolkata, so it's always a happy occasion to be back, albeit virtually, at my alma mater. With that, let me start. Let me start with the concept of first at the very beginning. Let me point out what we have done. So the system that we are studying, they are being continuously measured, and so they are highly excited. And also, these are then open systems. And in this study, we show that nevertheless, the experimental setup that we study can actually predict phase transition points in reasonable agreements with quantum phase transitions in the ground state. So this is what we have achieved in this project. So now let me start by introducing the idea of continuous measurements. By the way, so I would like to mention that if you guys have any questions, you could stop me in the middle, and I would like to have it as interactive as possible. But anyways, so let me introduce the idea of quantum measurements. So in a quantum measurement, you essentially are extracting partial informations from the system of interest continuously. So when I say partial, I mean almost zero. How do you do that? So you do that by dividing the full time that you want to study the system into small infinitesimal intervals, and then you perform weak measurements in each of these intervals. So if I have to explain continuous measurement in one line, it is like you put Schrödinger's cat in a closed box, then you don't look at it. You essentially just like make a small hole in the box, and then you tickle the cat once in a while, and then you try to infer whether the cat is dead or alive by listening to how loudly it meows or how loudly it purrs and things like that. So this will be one line explanation of such measurement regime. So to be more precise, I will start by explaining what a generalized measurement as opposed to the projective measurement regime is. And then as an example, I will consider this Gaussian quantum continuous measurement. So in a generalized measurement regime, you start with a meter or an apparatus, and you start with a system, and both of them have a priori wave functions of their own. And then in a subsequent time, the system and the meter are coupled, and then the combined system evolves together for a short time. And afterwards, you do a projective measurement with only on only the meter part. And say if the result is R, then that already fixes the conditional state of the a posteriori system in terms of this MR. And this MR, this operator, is the generalized projection, generalized measurement operator. So in a projection operator, in a projective measurement, this is a projection operator, whereas here it can be any operator, can even be non-Hermitian. And then the probability of obtaining the result R is given by this particular formula. Okay, so this is what this is. And then as an example, let's talk about this particular measurement, which is called a Gaussian quantum continuous measurement, where you measure a particular observable, which is a Hermitian operator. But in that case, you describe the conditional state, that is the a posteriori state of the system, in terms of this kind of a wave function, where you can see here I have pointed out what is the generalized measurement operator. So here K is the measurement strength, dt is the measurement time, and the measurement outcome, which I was calling earlier as R, is now I denote it as alpha, which is a continuous index. So another thing to point out here is that when K tends to infinity, this measurement essentially becomes a projective measurement. Okay, now again, I have introduced the formula for the probability. One can calculate the probability for measurement outcome alpha, and then this becomes this Gaussian variable. This is this Gaussian, this is clearly a Gaussian. And then, so correspondingly, then one can introduce a stochastic variable describing the continuous measurement record, which I call as alpha S. And that is then described like so, where this dW is the Wiener noise. So a Wiener noise essentially is a Gaussian stochastic variable with mean 0 and variance dt. So, okay. Finally, one more thing you can do with this conditional a posteriori state, which is that you can expand it up to order dt, and then you will obtain this, what we call a non-normalized stochastic Schrödinger equation in terms of this stochastic variable alpha S, which was the continuous measurement record. So this is the regime of Gaussian quantum continuous measurement. Very good. So now let me move over to our particular experimental setup that we studied, which involves a homodyne measurement. And so in this measurement regime, what we will do is that we will start with an atom light coupled Hamiltonian. And because this is a homodyne regime, this will involve a high intensity local oscillator. And then at the end, we will obtain a stochastic Schrödinger equation with Wiener noise that will describe this whole setup. So here I show you the picture for the measurement setup. And so here the probe laser, so the system is the system, so some atomic system that we want to study. And the probe laser that we consider is quite weak in intensity. So the job of this probe laser is to drive the cavity. And also we consider this cavity to be quite bad, so it leaks. So the only job of this cavity is to engineer this 1D spatial mode function in this atom light coupled Hamiltonian that I have written here. So here this atomic part can be anything. Say, for example, we will study this Bose-Hubbard Hamiltonian, and this A dagger, this corresponds to the probe laser essentially, which, as you can see here, this couples the atomic ground and excited states, and the coupling I consider to be a dipole coupling essentially. Then we also consider large detuning between the laser and the atomic excitation. So this then allows us to adiabatically eliminate the excited state. We also expand the atomic ground state in the one-year basis of the optical lattice potential. So this has an optical, the cavity has an optical lattice essentially. And that then leads to an effective atom light Hamiltonian. Okay. In here, what we are doing then is that we are sending in the probe, and then the light is coming out. We are then also mixing it with a local oscillator, and then we are detecting the photons in these two detectors, 1 and 2, for the duration dt. So this is our measurement time, so as to say. And to describe such a system, one starts with an a priori pure state, where this state alpha and beta, these are the coherent states describing the probe laser and the local oscillator. And such approximation, where I describe these two states as coherent states, this works well when the measurement time is quite small. Also, another thing to keep in mind here is that the probe and the local oscillator have same frequency, and as a result, so that's why we call this measurement setup as homodyne measurement. So if they would have had different frequencies, you would call this a heterodyne measurement, essentially. Very good. So the measurement outcome essentially is the photon number difference in these two detectors, so which I denote as K. However, the absolute number of photons detected in these two detectors is not available to us. So the information of M is not available. So as a result, essentially, to obtain the conditional state, one has to perform such partial trace-like operation where you sum over all the M's. Another thing is that we consider 100% efficient photon detection, and also that we assume that the effect of this 50-50 beam splitter here can be described using a unitary operator. And as a result, this conditional state can be written as an outer product of two wave functions like this. So this psi is the wave function corresponding to the conditional state. Okay, and this then we also we derive this, and then we show that this indeed this whole setup is actually equivalent to a Gaussian quantum continuous measurement, where this conditional state is described by this wave function, which I have already introduced in the context of Gaussian quantum continuous measurement. So we then redefine this K and the MR here a little bit, and then we can immediately write down a corresponding non-normalized stochastic Schrodinger equation that I have already introduced in the context of Gaussian measurements, which involves this continuous homodyne measurement signal in terms of the Wiener noise. And this Wiener noise essentially appears because you have this high intensity local oscillator. Another thing to keep in mind here is that this M naught that I am writing, so this is the so-called measurement operator, like observable that is being measured. So the matrix elements of this operator depend on the frequency and the phase differences between the probe laser and the optical lattice. So by changing these frequency and phase relations, one can obtain different observables that you would be able to measure. Okay, very good. So now let me also introduce the quantity of interest, which we call as the power spectral density of the homodyne measurement record. And we will show that the nature of the power spectral density drastically changes in different phases. And this particular criterion we use for detecting phase transitions. Okay, so let me first define, let me first explain how to obtain the power spectral density for individual quantum trajectories. And I will first define what I mean by power spectral density. So a power spectral density is the Fourier transform of the autocorrelation function of the homodyne measurement signal. So remember, this I is the homodyne measurement signal. But another thing is, here you can see that I need to integrate from over the whole trajectory. So for that reason, I will need the full history of the homodyne measurement signal. And to obtain this, one needs to essentially start from a particular pure experimentally prepared state, for example, the ground state, and then simulate the stochastic Schrodinger equation. And then by simulating the stochastic Schrodinger equation, you will obtain all this psi t plus dt's in all the subsequent times. And using the properly normalized state, then you can obtain the Homodyne measurement current as using this formula that I'm showing you. And then you plug it back in here in this formula and obtain the PSD. So this is how you obtain it for an individual quantum trajectory. And by individual quantum trajectory, what I mean is that one particular realization of this Wiener noise. So a given sequence of this dWt. So dWt is a Gaussian, is a stochastic variable which is Gaussian distributed. And so you choose just one number at each of these time steps essentially. However, one can now average over these noise realizations, and that will then obtain us something called this well-known Gorini-Kosakowski-Sudarshan-Lindblad type master equation in terms of this Lindblad superoperators. So here, this rho that I am writing, this is actually noise averaged density matrix. And now, if you recall the definition of the power spectral density, that involves this autocorrelation function of the Homodyne measurement signal. And this you can then obtain using the quantum regression theorem starting from this master equation. Now, to obtain this particular power spectral density using the master equation, we assume that at time t equals to 0, the density matrix was proportional to the identity matrix. So, oh, I have some question. Okay. No. All right. So, at time t equals to 0, we assume that the density matrix is essentially proportional to identity matrix. What that tells you, number one, is that at time t equals to 0, we are starting with a mixed state, unlike the case where we were starting with the ground state for the single trajectory. And another thing is very important. You see, although we are trying to predict ground state quantum phase transition, here the density matrix is having contributions from all the states in the spectrum because it's proportional to identity. So in this case, one can obtain the power spectral density, and the formula looks like this. So very good. So this is the quantity that we are going to study. So one thing to point out is that there is no reason to assume that these power spectral densities obtained from these two different approaches will be identical. However, we will show that the PSDs obtained from both approaches, they convey the same physics. And again, to reiterate, this provides a general criterion to detect quantum phase transitions in strongly interacting systems, which is that the nature of the PSDs are drastically different in different phases. Okay, so we studied two models, Bose-Hubbard and transverse field Ising model, and both of them can be written like so. So there are two parts, H0 and H1, and they don't commute. And both of these models depend on a single parameter, alpha, and there is a phase transition at a critical value of the parameter alpha c. And we will consider two measurement operator for each of these models. And so the measurement, the observable will commute with H0 in one case, and it will commute with H1 in another. So again, we will use Homodyne measurement scheme, and the models will be engineered using ultra-cold atoms in optical lattices. So here I'm writing the Hamiltonians for the two models. So for the first model here, in the Bose-Hubbard model, the parameter alpha can be thought of as the ratio between the interaction and the hopping strengths, whereas the parameter alpha for the transverse field Ising is essentially just the transverse field strength. One interesting thing to note here is that the Bose-Hubbard model that we consider is an ergodic system, whereas transverse field Ising model is quantum integral. This will become relevant later. And then I'm also writing the measurement operators that we will consider later. Okay, so let me just begin by considering this coherent measurement in the case of Bose-Hubbard model. First thing to note here is that this particular measurement operator commutes with the hopping part of the Hamiltonian, which incidentally has the superfluid ground state to be one of its eigenstates. And we see here, first of all, we see that the two PSDs are similar looking. I mean, although they are obtained using two different techniques, they look similar. And there is a very prominent peak at omega equals to 0 in the superfluid phase. And as you move over to the Mott insulating phase, you see that there are several peaks here. And the phase transition is approximately equal to U over J equals to 1. Now, if we consider this population measurement, which now commutes with the interaction part, we see that the prominent peak at omega equals to 0 is in the Mott insulating phase. And again, the phase transition is shown at approximately U over J equal to 1. So by looking at these power spectral density, we conclude that for an ergodic system, the power spectral PSDs obtained from both methods are quite similar, and the two different measurements detect the same ground state quantum phase transition. Now let's move over to a model, this transverse field Ising model, and this shows strong violation of ETH. And first, so here we consider this particular MX measurement, which trivially commutes with this transverse field part. And you see, first, you notice that the two PSDs are similar looking. And second thing to note is that indeed there is a prominent peak at omega equals to 0 in the ferromagnetic phase, which is the eigenstate of this particular measurement operator. And you see that the quantum phase transition is shown at approximately lambda equals to 1, which is also expected. However, when you consider this ZZ measurement, something strange happens, and you see that the two PSDs are not looking similar now. So this MZZ measurement, this thing commutes with this Ising part now. So you see the prominent peak at omega equals to 0 only in the GKLS PSD. However, in the stochastic Schrodinger equation case, there is no structure at all in the ferromagnetic part. And to explain this, we point out that the ZZ measurement has a special commutation property like this. And as a result, we think that this is a less effective perturbation for exploring the ferromagnetic state. And also exploring the full phase space in the ferromagnetic state. And moreover, the Hamiltonian has a special property, which is that there is no tunneling matrix element between the majority up and the downspin sectors of the infinite system at any finite order of lambda. And this, we think, explains why there is no peak at all in the ferromagnetic region in this particular PSD. Finally, to conclude, in a non-ergodic system like transverse field Ising model, the PSDs obtained from two methods are sometimes dissimilar. Nevertheless, they detect the same ground state quantum phase transition. Finally, I would like to touch upon the effect of measurement strength and how one can access the quantum Zeno regime. And to do that, I would like to consider the example of the coherent measurement for the Bose-Hubbard model. And I had already shown that when the measurement strength was 0.01, the power spectral PSD showed a phase transition at U over J approximately equal to 1 from the superfluid to the Mott insulating part. Now, if you consider the measurement strength to be quite high, that is 100, then you will see the superfluid phase all throughout, as you see in the right-hand side PSD. And this one can think of as a dynamical phase transition into the quantum Zeno regime. Okay, so to summarize, we have explored the complex relation between many-body dynamics and continuous weak measurements. And as a proof of principle, I have demonstrated that it is indeed possible to detect phase transitions by discerning qualitative changes in the measurement signals. And I would also like to point out that the measurement scheme that we consider is non-destructive, unlike the normally administered time of flight measurements, for example. So we think that our measurement scheme is useful for studying systems that include feedback control, which is very relevant for this particular summer school. And I also think that it can be useful when one needs to measure other parameters of a quantum system across a quantum phase transition where you cannot destroy the system. So with that, I would like to thank you for your kind attention. These are my collaborators. Lucas is in Switzerland now. Felix is in Forschungszentrum Jülich, and Klaus, Jakob, and Anna, all of them are in Aarhus with me here. And this is the name of the paper and the archive link. So thank you. Thank you.
Thank you, Dr. Patra, for this exciting talk. Any question? Yeah, any question?
Yeah, can I ask one question, Ayan?
Yeah, sure, sir.
Yes, please.
Very interesting and very intriguing that this quantum phase transition. How is it measuring? See, quantum phase transition is a non-local kind of behavior, no? Right?
Right.
So how is your for example, and I'm just curious. See this Dickey phase transition. This Dickey model.
Yeah, you mean like the super radiant phase?
Super radiant. So yeah. this way we can detect through super radiant behavior also. Huh?
We think so. I mean, like we are like these are very generic models, right? Like for example, Bose-Hubbard or transverse field Ising. That's why I showed that. First of all, these are many body models.
Right.
And
right.
One is ergodic and one is integrable. So it's like as different as you can get.
Correct.
And there is a lot to be studied actually. So you see that the PSDs obtained from the stochastic Schrodinger equation and the master equation, they look similar. And I also pointed out that when you consider the master equation, your initial condition was a density matrix which was proportional to the identity. So that meant that you are taking contributions from all the states. So, I mean, we have a rough picture, like you have an Arnold tongue, like, something that is happening in the ground state and then you have the signature in the spectral density. However, I think one needs to study it more closely as to how the information is spreading and how many states are actually participating, and how fast are they spreading and all this. So it's only just the beginning, and I mean, lots have to be actually analyzed now. So yeah.
Very impressive. Thanks a lot. Yeah. Okay.
Thank you. Thank you very much. Any other question? Okay, so I have a very small question, maybe very trivial. If you just go back to the first slide.
Okay.
Not first, means for second or third slide. Yeah. Just go down one slide more. Yes, here I don't understand in this if kappa, this k or kappa, whatever, if it is going to infinity, you are considering this factor e to the power of minus of 2 kappa. This factor is going to some.
So it's like a delta peak, essentially, or like
okay.
So what is happening here now is that So if you do so a rough picture is that when you do the measurement, so okay, let's start with a projective measurement. What does a projective measurement do? It gives you one, let's say you have multiple indices, right? Like 1, 2, 3 up to n. And you do a projective measurement and you get a result m. That means like you will have the eigenstate psi m out, and that's it, right? Whereas in this measurement scheme, what is happening is that like it's Gaussian distributed. So you have m, and then you have probability of having all the other states with like very, so that probability is very small. But then when this strength goes to very, very high, then you will only get m. Like it's the width of the Gaussian will become very, very narrow, and then that becomes projective measurement. So that's the picture.
Okay, thank you very much. If there are no further questions, let's thank Dr. Patra and for this exciting talk. And we move on to the next topic by Ms. Amrita Mandal from IIT Kharagpur, whose main interests involves quantum walks and combinatorial matrix theory. And I request Ms. Amrita Mandal to share her screen. Yeah, thank you.
Am I audible, sir?
Yeah, you are audible. Yeah, now you are audible.
Good afternoon. I am thankful. First of all, I am thankful to the organizer for giving me the opportunity to be present here. Today, I am going to talk about the localization of quantum walks defined by generalized Grover coils. I will follow these two articles to highlight some of the results I will be presenting here. So this is the outline of this talk. So first, we will introduce what is the generalized Grover walk, and then we will talk about the localization phenomena of such types of walks.
Can you kindly switch on your camera? Is it possible? Yeah, okay, thank you. Thank you.
So let's first have some basic idea about the mathematical description of permutation matrix. First choose three objects ABC. So what is the permutation? I give a new arrangement for this object ABC in this order BCA. So A is coming from position 1 to 3 here, and B is coming from position 2 to 1 here, and so on for the C, which is taking place from 3 to 2 here. So the underlying permutation which is giving this new arrangement is 1, 3, 2. Corresponds to a permutation matrix can be defined, which is basically a 0-1 matrix whose non-zero entries takes place in those places. Like for example, if I choose this permutation as 1, 3, 2, then the corresponding permutation having permutation matrix is having entries as the position 1, 3, then to this position 3, 2, and then 2, 2, 1. And this is another kind of important matrix which will be used in this presentation. So that is the permutative matrix. This is a matrix whose rows are permutation to each other. For example, consider this one. So the first row vector is 2, 4, 5. Then the second one is 2, 5, 4. Just the element 4 and 5 are exchanging their places here, and for so on for the third one. So this is a permutative matrix. So the talk will I will present in this way. So first we have the linear sum of permutation matrices, and then we will consider the orthogonality for matrices in these spaces, and all such types of matrices will produce the permutative orthogonal matrix, and we will use these matrices as quantum coins, and we will study for one important phenomena for quantum work, which is localization, using these types of coin operator. So at first, let us have some basic idea about a brief idea about what is quantum work. So quantum work is the quantum analogous part of classical random work. As like the classical one, so quantum work is also defined for both discrete and continuous time interval. And so quantum work on a graph is defined in such a way that at each of these vertex position of this graph, the quantum particle is in its localized state. And all these state vector here can span a Hilbert space, which is called the position space. And at each of these vertex position, the quantum particle can move from one vertex to another vertex, subject to the condition that these two vertices are connected. That is, there is a edge between these two vertices. Then after the coin flip operation has been done here, then according to the coin flip operator and based on their outcomes of the coin flip, the quantum particle can move from one position to another position, and this transformation or this shift will take place under the shift operator. Here everything S and C, everything is a unitary operator. So the total here, due to this outcomes of this coin flip operator, another kind of Hilbert space is generated here, which is called the coin space, and the total space is thus is the tensor product of the position space and the coin space. The evolution of this work is thus defined by this quantity, and the quantum state of this worker is given by this rule, where U is the unitary operator and psi naught is the initial state vector. So I would like to highlight some basic difference between classical one and quantum discrete time work. So in this case, for classical work, the local transition probability is stochastic, but here as we see that this is a unitary matrix, here the probability distribution is diffusive. For example, if we choose our coin operator to be a Hadamard coin operator, then we see that this red dotted color describe the probability distribution for the corresponding work, but this blue colored line describe the probability distribution for quantum work. And here we work with the probabilities, but here due to this additional Hilbert space, which is due to the coin space, we work here with the probability amplitude vector. So for classical, here we see that after many iterations, the classical worker path can be decided on a decision tree in a unified way. But here the worker spread throughout the lattice as like a wave function, and we need to collapse that wave function at last of this work. So these are some, so the question arises that why should I study further quantum work over their classical counterparts? So quantum work is the powerful tool to build quantum algorithms, and there are many practical problems like which shows that the quantum algorithm could give polynomial speedup over their best known classical algorithm. For example, the element distinguence problem. This is the problem to find that whether for a given set of large data, all the elements are distinct or not. And another kind of problem is the triangle finding problem. This is the problem to find a triangle or a tree cycle for a given large graph. And such kind of polynomial speedup, and there are also there are also studies who show that for some cases this speedup also going take place for exponential order, shows that the quantum computers, which is basically based on quantum algorithm, could give rise to excellent performance rather than the best known classical computers. So one type of such known quantum algorithm which is very popular in literature is the Grover algorithm, and it is proved that the Grover algorithm could give polynomial speedup over the best known classical algorithm. And the Grover diffusion matrix is arise in case of this Grover algorithm, and it is extensively studied for culture the many quantum walk phenomena with this Grover matrix used as a coin operator. So let us recall that the Grover matrix of order 3 and order 4 looks like this form. So both these matrices are symmetric, and they are the orthogonal matrix, and the general form can be described in this manner. So where Jn is the all-one matrix, and we made two important observations on the structure of this matrices, that both the matrices can be written as the linear sum of permutation matrices, and point two that these matrices are the permutative matrices, that is rows are permutation to each other. So based on these two important observations, we motivate to study for choosing the orthogonal coin operator, which are either linear sum of permutation matrices or permutative matrices which are orthogonal, to generalize the concept of the Grover matrix, as well as we can generalize the Grover walk concept. So the parametric representation of all such types of matrices could give the idea that how the parametric value is influencing the quantum walk phenomena with the change of this parameter. And since discrete time quantum walk is can build a universal model for quantum computation, it is obviously of all paramount interest to study the properties of discrete time quantum walks, especially for with parameterized coin operators. So our first focus is to find the generalized Grover matrix. So according to this theorem, first of all, let us introduce that this PO3 denote the permutative orthogonal matrix of order 3, and then this theorem characterize all such matrices in this set, which says that matrices in these classes takes either this form or this form. So both these matrices can be written as the linear sum of permutation matrices, and there are several other group of chains of such matrices, and here according to this theorem that the linear sum of permutation matrices and the matrices here will characterize the same set of orthogonal matrices. Here I would like to highlight some generalized Grover coins which can be produced from this classification. Here we see that the theta is the parameter here, and all the diagonal entries are same here. For example, if we take theta is equal to pi here, so the diagonal entry will become -1/3, and all the rest one will become 2/3. So this matrix will then reduce to the Grover matrix of order 3. So we can consider this parameterization form as the generalization of this Grover matrix. Now in quantum direction, our problem is to find the limit theorems with these generalized Grover coins, and from that aspect we will analyze the localization phenomena, and in another direction we will derive the peak velocities and also study for the same thing. So at first I will introduce for three-state quantum walk on a line. So here the vertices on a line is labeled as the integer value, for example 0, 1, 2, -1, -2, so on. At each of these vertex position, the quantum particle can move to its right vertex position or to left vertex position, or it can stay to its original position. So there are 3 coin state here, hence the coin space has dimension 3 and it is isomorphic to C3. And due to this position space, which is labeled as the jet plane, our position space is isomorphic to Hilbert space small l to z. And here the shift operator is acting on the particle position m, which is responsible for a left shift, for a right shift, or it can stay to its original position conditioned to the coin state vector 1, 2, or 3. These are the standard order basis of this space C3. And here the state vector at time t can be described as the linear sum of this quantity m tensor product L. This actually span the whole Hilbert space H here, and the probability amplitude vector, which is taking the important role for describing the probability of this particle at the position m and at time t, is this vector quantity. So
sorry, Amrita, can I ask a question? So generally in Grover's algorithm, you have n elements, right? And then you are trying to select one out of them. Yes. So, right. So here, what are those? What is that space?
That is the small l to z.
Sorry, I couldn't hear you.
Small l to z space, the Hilbert space.
So the full Hilbert space is this I2Z cross with C3. Is that what you're saying?
That is the total Hilbert space. This is coming from the coin operation, and that is due to this position 0, 1, 2, that whole extended infinite plane.
I see. And then what is the element that you are trying to select by doing this, by using this algorithm?
I mean, you are trying to say that we are taking here a QIQT here, so the quantum particle. Yes.
Okay.
The probability of finding the worker at a time t and at position m is defined as the inner product of this probability amplitude vector, that is the norm of this probability amplitude vector. Then the localization concept come from this definition, that the work is said to be localized at the position m if there is always a non-zero probability of this particle to stay at the position m even after infinite time intervals. So there are many studies has been done for localization of Grover coin and for localization for Grover work, and also for localization of generalized Grover work with other set of coin operators. So here we recall that we will study for localization with the new type of generalized Grover coins, whatever we have derived. So we recall that these are the classes we are going to study, and we describe the first we describe the limit distribution, that is the approximation of this value of the probability to find at the position m by that quantity, and where the initial state vector is alpha, beta, gamma. And for time being, I am skipping the detail of this statement. For a better visualization, let's have this figure. So here, this blue bar quantity is coming due to the approximation of the probability, whatever we have derived in the previous theorem. And these black circles are coming from from the probability value with a large value of t, which is 5,000 here, and we see that this approximation is matching nicely with the finite large t. And here also one point to be noted that this probability quantity could be 0, and the initial state vector is taking important role here. So based on this initial state vector condition, we can have the work which delocalizes. Here we see that for the generalization of these Grover coins, here the coin operator is changing around along the ellipse. So here we see that at each of these coin parametric value, we compare the quantity with the finite large t with the approximation we have derived in this theorem, and it is in the y plane, and for giving a transformation by this quantity, we see that in the theta plane it is it can be compared in this way, that how for each theta the value of large t with large t and the approximation value can be compared. Then we will study for another from the localization in another aspect, that is for after deriving the peak velocity. So that is the this quantity is the eigenpair for the evolution operator u tilde, that is the evolution operator which can be obtained from the original evolution operator u after Fourier transformation. So here we recall that the probability amplitude vector can be described in this way with the help of this eigenpair and the initial state vector. That's why the initial state vector and eigenpair is playing important role for describing the probability for this particle. So here we say that the probability for right going peak can be described by this quantity, and the left going peak is described by that quantity. So here k0 is the critical point for which this second derivative quantity is becoming 0. So then the peak velocities is given by this quantity. So after plotting this, we have the velocity is taking this part. And then we will see in the next slide that how the peak behaviors is getting changed with the change in the time. So here we see in each of these figure, it has 3 peaks: the central peak, one right peak, and another is the left peak. So when time increases, we see that these peaks travels, and it travels away from their central position, and it is around at the particle position at 60. And when time is large enough, near about 500, then we see that the peak is at around 300 positions. So and another thing to be observed, that the probability value is getting very less when the time quantity is getting larger. So here we see that the probability is very small compared to these two quantities, and the interesting thing to be observed here, that the central peak does not travel, and we see that the central peak is there in all the figures. So this central peak says that there is always a non-zero probability of this particle to stay at the position at the central position 0. So this actually indicates the localization of this work. And here we mention that it is needless to mention that we choose the initial state vector to be this vector. So as a conclusion, we say that the Grover work localizes, but we have extended this Grover family, Grover coin operator, to a large collection of coin families, and for that case, we also we are able to show that the localization phenomena also is satisfied for all the works defined by the coin collection. So these are some references I would like to highlight, and Thank you for your attention.
Thank you very much. And so the session is now open for questions. Yeah, Dr. Patra, please go ahead.
So I'm still trying to understand, trying to compare it, because I only know the Grover algorithm from, like, the original one, where you get the quadratic speed up, etc. So do you not then study the quadratic speed up?
No, sir, I have not studied for that. I collect that result from some paper, that this one.
So yes, what did you collect? So you say that whatever your model that you are considering, that indeed shows polynomial speed up. Is that the claim?
No, sir. Sir,
No?
no, sir. I have not studied for the time complexity here, but we study for the localization concept only.
Right. Okay. And do you know, so you showed the final picture of the probabilities with all the peaks. So I would like to know what was the initial, so you started at time t equals to 50. Yes. How did the probability distribution at time t equals to 0 look?
No, sir. Actually, I take the snapshot for time 50, 100, and 500, and the work actually in general starts from the time t is equal to 0 here. And
no, that is what I was asking. So how does the probability distribution at time t equals to 0 look?
Yes, sir. So in that case, the particle is actually in its original position only. So this distribution will not take place. Then we cannot see the right hand and left hand peaks here. Only there is a probability for staying that particle. It is basically is taken that there is a probability 1 to for this particle to at the initial position when time t is equal to 0.
And final question, so can you, like, here you have just considered a discrete unitary evolution. So is there, do you know of any references, or maybe you have studied yourself, where they write Hamiltonians corresponding to this, or no?
Yes, sir, they are also working for continuous time case. You are saying about that, for that?
Yes, exactly. So I'm asking if there is a Hamiltonian which I can then use to study, like, other localization properties.
There are also parallel study for the continuous cases for the localization or all these cases. So in that case, the adjacency matrix is taken to be the Grover matrix or any other kind of 0-1 matrix for with respect to the given graph structure on what they are studying.
I see. Okay. Thank you. Very interesting.
Any other question? Yeah, if there are no further question, let us thank Ms. Mandal for this very intriguing talk. Thank you very much. And actually, at this moment, I would just like to take an opportunity, as just before that, Dr. Patra was mentioning something. I would like to just have a short discussion, if you don't mind, on that. So you are talking about the implementation in the cold atomic system. So what kind of cold atomic gases you are experimentally means you have planned to use? Or
you mean
the experimental front
with my systems?
Yeah.
That I don't immediately have an answer for you. Okay. But I think this type of, like, Bose-Hubbard models, etc., these are routinely implemented.
Yeah.
Using,
so means,
for example,
in the experimentally, so to do it in the means say lithium, sodium, means any experiment already done, or it is in the future?
I don't think any experiment has been done on this.
Okay, okay.
So we are proposing this.
Okay.
Yeah, so there is no experiment
Okay.
because most of, like, I mean, it's so people generally just study these phase transitions using time of flight measurements, right? So they don't need to. So it was like a proof of principle kind of thing that we wanted to put forward.
Okay.
So I think it can be seen. It should, like, if our things are correct, and I assure you that I have gone over all the calculations and my numerics multiple times. So if everything is correct, then this should work out.
Okay.
But in the experiments, experimentalist is the king. So
yeah, sure.
If it doesn't
These
work,
are
then
very
it doesn't
these
work.
are very involved experiments. I understand.
Yeah, no. So then I'll have to go back and find out exactly
I
all the
understand.
things.
Okay, thank you very much. Okay, so let us now move on to the next speaker, to Dr. Avijit Mishra.
Yes, I'm here.
Hello, good
Hi.
afternoon.
Yeah.
So, Dr.
Am I
Mishra,
audible?
Yeah, you are audible. So Dr. Mishra did his PhD from HRI, and he is currently now postdoc at Weizmann Institute in Israel. Previously, he was also associated with the International Center for Quantum Artificial Intelligence of Science and Technology at Shanghai University. And his research interest includes quantum information, quantum thermodynamics, dissipative quantum systems, and so on. So let us now welcome to Dr. Mishra for his lecture.
So I'm sharing my screen.
Yeah, sure. Please go ahead.
Okay. Hello. Can I start?
Yeah. Please go ahead.
Okay. So I've been already introduced. So I'll be talking about work generation from thermal noise by measurement and discuss the role of information in it. The work was done in collaboration with Professor Thomas Opatny from Palacky University, Czech Republic, and Professor Gerson Kurisky at the Weizmann Institute of Science. Okay, so here's the plan of my talk. First, I will give brief motivation of my study. Then I'll discuss about work extraction in optical setup by phase-sensitive Homodyne measurement. And we all know that when we have optical system, we are inevitably associated with noise. So I'll discuss the impact of noise. Then I'll impact the effect of coarse graining. So if we don't have fine grain measurement, then what is the case? Then I will discuss about, instead of homodyning, if we do photo count, so what are the possibilities? And all this measurement based engine scheme, it is irreversible. We all know, because measurement is irreversible. So I will discuss, I will compare our study with reversible scheme, which is mostly efficient. Then I will conclude. Okay. So you all know that recently quantum thermodynamics has attracted a tremendous attention, especially quantum heat engines and refrigerators. And among quantum heat engines, information engine is one of the important aspects. So here we propose a novel method based on optical setup, but it can be used for continuous variable system also. And it is, we'll extract the work by observation and
Hello, Dr. Mishra. Dr. Mishra? I think there is some connection issue, so I request the audience to please keep patience, and he will be come online soon. Yeah, I think Dr. Mishra has lost the connection. Yeah, let's wait.